In this video, I want to discuss a useful theorem with regards to work and energy, and I also want to define what physicists mean when they use the term power. Okay, so now if this wasn't made clear before, let me define what I mean by the total work or the net work. Okay, the net work is the force due to or is the work due to the net force. Okay, so it's the component of the net force parallel to the displacement. We'll call the displacement distance d. Okay, so or you can call it work total equals a component of the total force in the direction of the displacement. Okay, now it turns out that if you're working with the total force or the net force, there's a useful alternative formula you could use to find the work. Okay, now to derive it, I'm gonna, for simplicity's sake, I'm gonna assume that the net force is in the direction of the displacement, so that the parallel component is the magnitude of the net force itself. Okay, so net work equals the net force times d. Now, if we are working with the net force, then we know that Newton's law says that that's equal to the mass times the acceleration. So look, now we have MAD, or MAD. Okay, we further know that if the the following result is true even if the acceleration wasn't constant, but I'll derive it assuming that the acceleration is constant. It'll be true in other cases as well. We know that for a constant acceleration, we have the kinematic equation that the change in the square of the velocity is 2 times the acceleration times the displacement, which in this case is d. Okay, so solving for the acceleration from that kinematic equation, we get delta v squared over 2d, right? Now let me substitute that into what we have so far for the net or the total work. So delta v squared over 2d times d, and then I can cancel out the d's, so let me move the 2 out, so let me multiply everything by 1/2. 1/2 m times delta v squared, so that's 1/2 m v final squared minus 1/2 m v initial squared, which, if you remember your kinetic energy formula, that's equal to the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. So apparently, if you're looking for the net work, where the force is in the direction of the displacement, you can simply calculate the change in kinetic energy, and you'll have your answer. You don't have to bother with finding the net force and multiplying it by the displacement. Okay? Let me give you an example where this is useful. All right, suppose you had to solve this problem. A 2,000 kilogram rocket in outer space at rest fires its thrusters until its velocity reaches 1,000 meters per second. Okay, how much work was done by the thrusters? So we're in outer space, so there's no gravity, and the only force is the force due to the thrusters, so that's the net force. So we have a situation where we could use the result that the net work is equal to the change in kinetic energy. And By the way, this useful result that I just derived is called the work energy theorem. Okay, so I'm going to use, and this is a situation where we use the work energy theorem. So the work done apparently is equal to the change in kinetic energy, which is 1/2 times 2,000 times the final velocity squared minus the initial, which was 0. So we can work that out. So this is equal to 1,000 times 10 cubed squared, which is 10 cubed times 10 to the 6, which is 10 to the 9. So we have 1 billion joules, or if you want to be fancy, 1 gigajoule. So it did 1 gigajoule of work. Okay? Imagine that you didn't have the work energy theorem. You would be stuck trying to figure out, okay, what is how many newtons of force are the thrusters providing? What distance did the thrusters move the rocket, right? Because you would be trying to use the work formula involving force and displacement, okay? The information is all in there. If you are clever, you could use the kinematic equations and figure out the answer, okay? The work energy theorem, it does all that work for you, okay? And it arrives at this wonderful result. So I've given physics tests where people will come up to me and say, hey, you didn't give enough information to find the work, because they think that they need to use the formula involving force and displacement. And I'll say, nope, you can solve it, and then they get frustrated because they forgot about the work energy theorem. All right? So there you have it. There's a wonderful example. Okay. Now, in addition to talking about the work involved in a certain process, people sometimes want to know how fast was work done. Okay? So when people want to talk about how fast was work done, the rate of doing work, that is what power is. Okay, power is how much work you do divided by how long it takes you to do it. Okay? And the units of work are joules. The units of time are in SI units. The preferred units are seconds. So power can be given in units of joules per second. Okay? Now, another name for joules per second, we name it after a famous scientist who studied steam engines, watt. So we give it in units of watts. Okay? So, for example, suppose the whole process with the rocket took, let's do a couple of different examples. Let's say that it reached 1,000 meters per second. Let's say it took 1,000 seconds. Maybe for a different rocket it took 100 seconds, 10 seconds, and maybe we had one that had hyperdrive or whatever fancy thrusters, whatever you call them, whatever you want to call them. Let's say it could do it in 1 second. Okay, so for the 1,000-second situation, well, we had a gigajoule divided by 1,000 seconds, so that's a 10 to the 6 joules per second, or as I said, you can call that watts. So 10 to the 6 watts, or even fancier, 1 megawatt. Okay? The 100-second situation, there you have 10 to the 9 divided by 10 squared. That's 10 to the 7 joules per second, or 10 to the 7 watts, or 10 megawatts. Now, what's interesting is that the work was exactly the same. Okay, whether it took 1,000 seconds or 100 seconds, you still did the same amount of work, 1 gigajoule. However, the power is not the same. Okay, so you can have situations different power, but same work. Okay, and then for the 10-second situation, 10 to the 9 divided by 10, 10 to the 8 watts, or 100 megawatts. And then the last one would be 1,000 megawatts. Maybe I'll do that in back. Okay, I'll let you work that the other details out of that if you wish. Okay, so all the same work but not the same power. Now, when you think of watts, you probably think of light bulbs, 60-watt light bulbs, 100-watt light bulbs, etc., etc. Now, light is giving off a certain type of energy that we haven't discussed yet. It's electrical energy, okay? And so what a 60-watt light bulb, electromagnetic energy actually, what a 60-watt light bulb is doing is it's belting out, it's giving out 60 joules of heat every second. Okay, that's why you have to pay your utility bill.